Well, I have 12 o'clock, so I will go ahead and kick us off here. I had a few of our friends let us know that they were going to be in Florida this week during the presentation, and I did let them know it was a Zoom so they could still join us and maybe bring us some of that warmth. So we shall see. But I just want to thank you all for being here. This is our fourth Library Lunch and Learn series of the year. I am Amy Pett, the Executive Secretary of the Friends of the Alexander M. Bracken Library. And the goal of this series was to highlight some of the just really transformative research that our faculty are engaged at here at Ball State, and then to really foster collaboration from a variety of different vantage points and research perspectives to really engage in interdisciplinary dialogue and help grow our knowledge of different areas. So I'm really pleased to share in today's conversation, and I will now turn it over to Nick to talk a little bit more about our speaker today.
Thank you very much, Amy. So I'm Nick Havranek. I am the Engagement Strategies Coordinator for University Libraries, as well as the Assistant to the Executive Secretary of the Friends of Bracken Library. Um, and just really quick, I think everyone should have been notified, but this meeting is being recorded and it will be uploaded to the University Libraries YouTube channel where we have a playlist of all the past events. And so without further ado, I will introduce our guest speaker. This is the Spaceflight and Astronaut Health Insights into the Benefits of Exercise event. Dr. Todd Trappe, Professor of Exercise Science in the Human Performance Laboratory and part of the School of Kinesiology and College of Health, will discuss the research that the Human Performance Lab has been conducting with the National Aeronautics and Space Administration over the last 30 years. He will specifically address the challenges to astronaut health during long-duration space missions and the role of exercise in maintaining astronaut health. A little bit about Todd's history. He has been with the Human Performance Lab as a faculty member since 2004. He received his bachelor's from the University of Iowa and master's from the University of Colorado in conjunction with the United States Olympic Training Center in Colorado Springs. He then earned his PhD from Ball State University and completed a postdoctoral fellowship in aging and metabolism at Penn State University. Prior to returning to Ball State, he was an associate professor of geriatrics and physiology and biophysics at the University of Arkansas for Medical Sciences. His research interests in astronaut health, intersect with his related interest in healthy aging and the influence of exercise. So without further ado, I will hand things off to you, Todd.
Thank you, Nick and Amy, and everyone for coming to the talk or tuning into the talk. Hopefully today I can provide a bit of a balance between educating you a little bit about some aspects of spaceflight as it relates to health, the role that exercise can play in maintaining health when you're in the spaceflight environment, and what that means really for people that are interested in being active on Earth. I think there's a lot of application in that regard, and we'll touch on that briefly. And hopefully we can also provide a little bit of insight as to the adaptive response to exercise. What does that really look like? Why do we exercise? How long does that last? And how powerful is exercise? And so with that, that's kind of the two main talk goals. And hopefully we can achieve those. If you have any questions, I don't know if I'll see everybody's hand, but I'm happy to keep an eye on things. Maybe if Nick sees a hand go up, we could address questions as we go. I'm happy to do that, but also I know we have a Q&A at the end. So to provide a little bit of background to any of you on the the call that are not familiar with the Human Performance Lab and its involvement with NASA. So you'll see HPL throughout the talk for Human Performance Lab here at Ball State. We got involved, and actually, let me maybe ask Nick or someone, can you see my pointer as I move around on the screen?
Yeah, I can see it.
Okay, good. Um, so the first space flight that we got involved with was back in the early to mid 1990s, preparing for it. It happened in 1996. And you see these badges here, this picture, this is classic NASA. They have a badge for each mission, and they started this way back at the very beginning. So every one of these badges you see throughout the talk reflects a space mission that we've been involved with. So we started back in the 90s. And along the way, we've been involved in a series of bed rest studies, and we use bed rest, and NASA uses bed rest to simulate being in space. So when you lay down and you stay laying down 24 hours a day, 7 days a week, it simulates the effects of being in microgravity. And so you see a lot of deconditioning and a loss of physical function and other things that we'll talk about today. But we were involved along the way here where we've learned a lot of these things that we'll talk about today in bed rest studies. That this first one was linked to the spaceflight mission of the space shuttle. And back then it seemed like they were long missions. We were on the longest mission at the time of 17 days, but that's quite short. And so this was a 17-day bed rest study. But we've done 60, 90, and then another 70-day bed rest study where we've actually, people are in bed for 2, 3 months, 24/7. Everything is done horizontal. And so we'll talk about that a little bit. And that's provided us a lot of scientific insight along the way. Interesting studies to do. I'm happy to discuss things about those studies. And then these are all of the space station studies, which the space station started around the year 2000, being inhabited. And these are all the individual missions that we've been involved with, studying crew members flying on the space station. And on average, it's been about 6 months for every crew member that's on the station. So a lot of information. It's kind of slow going. This has been, 30 years in the making, but we'll talk about some of the things that we've learned about. And so one of the real hallmarks of the research that we do here at the Human Performance Lab as it relates to astronauts, but also to primarily aging individuals, to some degree, athletes. The original charter for the lab was, the Human Performance Lab. That's taken on a little bit different meaning now, but it still kind of fits with our interest in understanding individuals as they function, kind of, if you will, at the whole body level, the classic just functioning in the environment and maybe competing if we're talking about an athlete. But this is one of our subjects on the International Space Station, Reed Wiseman. We'll talk a little bit more about Reed, but he's running on the treadmill on ISS. But what I'm showing here is a couple slices, if you will, that where we want to look at the individual muscles of the legs. The legs are by far the most influenced muscles when you go to space. They really deteriorate. And so this is an MRI image of a cross section, as if you took a slice right through the middle of Reed's thigh. In the front is the quadriceps muscle, and the back are the hamstrings muscles. And so we're interested in how does the whole muscle change in size and in function, but we're also interested in inside the muscle. And so we go in and we take a small piece of muscle from individuals, including the crew members, and we can get a small amount of muscle tissue. And here, this is a whole bunch of muscle fibers, and each muscle fiber is like a human hair. It's about the size of a human hair. They're quite long, much longer than this, but this is a small segment that we get. And we can go in then, and with some forceps, we can isolate out individual fibers. And so you'll see a little translucent fiber get pulled out, and that's one individual muscle fiber. And then it can get put on a special apparatus that we have here in the laboratory, and it can get tied off on both sides. And effectively, we can determine the same exact kind of things that we do with individuals in the lab where we want to figure out how big their muscles are. We want to figure out how strong their muscles are, how powerful they are. We can do the exact same thing at the individual muscle fiber. And so this is a muscle cell, essentially. And so we can figure out if the muscle fibers got bigger or smaller and see how that compares to what we see with the MRI images of their whole muscle, how powerful they are. And this is independent of their input, right? They're no longer connected to this fiber. So we can look at the maximal ability of the fiber. And really what we're interested in is, can we maintain that with an exercise regimen? Our goal is to make their muscle stay as healthy as it was when they launched into space. In the case of aging, we're interested to see if that would, if we can improve someone's muscle health with aging all the way down to the individual muscle fiber level. And the other thing a couple other things we like to look at is what we call the mitochondria. This is commonly referred to as the powerhouse of the cell. This would be like the coal-fired power plant, or maybe in this day and age, the nuclear plant, or a bunch of windmills as you drive up to Chicago and see all of those. But this is where all the energy is being generated. So we're interested in the enzymes, the proteins inside these mitochondria, and if we're maintaining them so we can actually generate energy to support exercise at the same level all throughout the mission. And then we want to also look at the capillary supply, the individual microvessels, and you can see those as little black dots that surround these individual muscle fibers. They deliver blood to the muscle. So we want to know, if we go back here, the whole muscle size and function and power, how is it being maintained, all the way down to the individual muscle fiber size, force, power, the powerhouse of the cell, the energy producing capabilities, and then the blood supply. Can we keep that intact? Because all of these things degrade with inactivity, and they degrade at a very high rate when you go to space. And the reason that we're interested in looking at the individual muscle fibers, each of these segments here, if you can kind of see the border, are individual muscle fibers. We have two different types of muscle fibers, and we call those the muscle fiber types. The black ones here are what we would refer to as slow twitch or endurance type fibers, and the white ones are considered fast twitch or high power producing type 2 muscle fibers. And so we want to know if our exercise regimens are maintaining each of those different types of fibers appropriately, because they both degrade differently as you float around in space if you're not doing anything. So I don't want to get too deep into all of the different bars here, but what I want to highlight is the other element to think about as we try and design exercise programs for astronauts and for older individuals, or for the rest of us on Earth, is what happens when you do one session of exercise. And if we think about our DNA and all the genes that we have that encode for all the signals that allow us to adapt. And it turns out there's about 20 to 25,000 different signals that can be turned on, and we call those messenger RNA. And it's generally referred to as transcription. So there's about 25,000 of these inside your muscle cell, in each one of those muscle fibers, just floating around ready to do something at different levels. And the key to this whole slide is not the individual names of myostatin, TNF, interleukins. That's not the goal. The real goal here is to just look at the timeline. And you can see before exercise, if we take a muscle sample from an individual and we measure the level of these different signals, you can see that they ramp up after running this is a 30-minute run, or a 30-minute run, or after a very brief couple minutes of high intensity weightlifting, resistance exercise. You can see that these signals get turned on, they get ramped up within an hour or so, and most of them last for at least 24 hours. And you can see, and this is just 4 of the 25,000 of these that are available in the muscle cell. So it's a long-lasting signal. So a lot of people want to exercise every day or twice a day for some of the athletes, but the signals from every time you exercise actually last for several days. And they turn into individual proteins. And so this is another way of looking at this is the next step in the kind of biological process. We call it translation, where all of those individual signals coming from our DNA and from our genes get turned into proteins. And so if we do a single session of aerobic exercise, you can see this is muscle synthesis rate. So the rate at which we're building new proteins inside our muscles. And that could be new proteins for those mitochondria, the powerhouses of the cell, or it could be new components that build your muscle and make them bigger if it's resistance exercise. But you can see under either type of exercise stimulus, the signal is lasting for at least a couple days. So that gives us a lot of good information for programming for crew members. How frequently should we have them exercise, and how long is a signal last before we need to kind of ramp the signal back up again? So just keep that kind of in the back of your mind as we move into the discussion on this. And then the other concept to highlight is, I kind of alluded to it. So here on the right is one of the crew members that was a subject for us, Mike Fossum. He's floating in space, and you can see that there's really no reason for his muscles to really do any work. He's just floating around. He can move throughout the space station with the tap of his hand and very, very little muscle activation. So if he doesn't do any scheduled exercise, he will deteriorate rapidly. And so if you look here on the lower right, this is an MRI image of a slice of the thigh, like I showed you from Reed Wiseman earlier, where the front of it is your quadriceps, your thigh, the back is your hamstrings. This is the typical image of a 25-year-old. This is a typical image on the right of that of a 74-year-old male that's healthy. They've got a little more fat. That's the white part around here, but you can certainly tell without any fancy instrumentation outside of the MRI is that the thigh muscle is clearly much smaller. And on average, if you take huge numbers of 20-year-olds and huge numbers of 75-year-olds, you will get a difference of about 20 to 25%. That's about how much muscle mass we lose in 50 years of aging. Well, if we do controlled bed rest studies with individuals that don't do any exercise, that's about how much muscle mass that you lose in a couple months of laying in bed 24/7, or what we would say simulated microgravity. So we never send anybody to space that never does exercise. So all of our absolute no exercise studies are always done simulated on the ground. But you can see that if Mike didn't do anything in space, he's going to age, at least the mass of his muscles is going to age about 50 years in just a few months. And this is 2 months of bed rest. And these guys are up here, the men and women are up there for 6 months. Now we're moving into a year. If you think about Mars, it's probably going to be a couple year venture. So there's a lot of signals to say, hey, we don't need much muscle mass around, and a lot of other things in your body that are really degraded when you're in space if you're not doing some exercise. So shifting gears to think about how NASA has tackled the exercise issue in space. The first person to exercise in space was John Glenn. For the older people on the call, you will know him from his space flight, or maybe even as a senator from Ohio. But he was the first one to fly in space. He was also the first person to orbit the Earth. And so on his first orbital mission, about a half hour into the flight, about 20 minutes into the flight, they had him drink some water with a sugar pill. They wanted to see what would happen if you ate some food. Would it even make it to your stomach? They actually didn't have any idea if you could eat food and then would it get stuck in your throat. And so that worked. So then they moved into the next thing. And the next thing was this exercise device. It was bolted to the floor here with this bottom part, had a handle on it for him to pull up. And he just simply did 30 repetitions of this, and they monitored his heart rate, asked him how he felt. They just absolutely had no idea what would happen. And so they realized, yeah, I guess apparently you can exercise. His heart rate went from about 100 up to about 140. So it was clear that he survived the exercise, and that's again back in the early 60s. So then we moved to the moon missions that happened not long after that on the Apollo rockets here on the left. This was the high-tech exercise device that they sent to the moon It was a 3-day trip. So on the way there and on the 3-day trip back, they were using this. They would attach this to some part of the inside of the capsule. There wasn't a lot of room. And they simply would put their feet or their hands in these loops and pull the rope through. You can turn this. You can see there's some numbers there, and the resistance would go up. And this would get exceptionally hot because as you pull the rope through, there's a ton of friction or resistance. And that was the extent of the exercise devices for the moon missions. And after the moon missions, then they moved into the first space station that flew for the United States. And actually what this is here is the core section of one of the Saturn rockets. So they built a whole bunch, but the Congress shut the program down. And so they had some extra rockets. So they took the core without any fuel tanks or anything inside there and turned it into a space station, launched it into space and turned it into a space station. For a couple of years, they did what were the first long duration, several month flights, and they had to develop some new exercise equipment. So the first set of resistance exercise, the first equipment that they used for resistance exercise was actually some springs that they purchased at Sears. And you can see the individual going through resistance exercise during long duration space flight. This is a 3-month, one of these was a 3-month flight. You can see how spacious the space station is. This is the whole core of one of those NASA Apollo rockets. But that's the extent of resistance exercise in space in the 70s. And they flew two or three of these in case they broke. But that was they literally just went to Sears and bought it. This was also the era where they introduced Teflon. And so they figured they could maybe create something like a treadmill if they had some bungee cords and a harness to strap the person down, if they coated a piece of metal with Teflon, they figured that that might work as a treadmill. And it turns out that it didn't actually work very well because the friction between the socks and the Teflon were so great that once they started to try and run on this thing, it just heated their feet up too much, and ultimately they never really used it for a treadmill. And then probably the most robust device that they did develop was the cycle ergometer, a bicycle. And you can see this individual's got some hoses in their mouth. This is exactly the type of thing we would do here in the Human Performance Lab, measuring their oxygen consumption and carbon dioxide production. Have some ECG leads on to measure their heart response. And you can see the individual exercising on the bike. One thing you will notice is that there is no seat. There's no need for a seat. His head has some padding up here to keep him pushed down, but there's no actual seat on the bike. And so they did a fair amount of cycling exercise as part of their countermeasures to prevent deterioration of their health. And so that leads us to, I'm skipping over the space shuttle era because all of those flights were so short that the amount of physiological deconditioning and loss to your health was certainly measurable, but it was nowhere near what it is when you get into the multi-month or year-long missions. So I'm dividing this up into the first decade of the space station. The Human Performance Lab was involved intricately in that first decade in documenting what was happening to astronaut health. And so the original exercise on the International Space Station, or the ISS, that was implemented was a bicycle ergometer here on the left, and I'll show you a little video of this. Very robust device. It's still the same device that's used today, almost never breaks down. But they had what they called an interim resistive exercise device that had some rubber devices inside that provided some resistance, but it was very low resistance. It was not really classic weightlifting as you think of it. And then a treadmill they called T1, the first version of the treadmill. A variety of exercise was done, but the individuals have 2.5 hours a day dedicated to do exercise. And for the first 10 years on the space station, most of the crew members would spend most of that 2.5 hours exercising. And for any of you that are active, you know that if you're going to exercise for a couple hours a day or more, you're not doing it at very high intensity. There's some real benefits for it of doing that, but it may not be the type that's beneficial for the crew members. So here's Don Pettit. He's been a subject for us a couple different times on long duration missions. And so you can see Don is floating along, riding in space. And one thing you will see in all the exercise videos is the importance of isolating the movement and the forces that are generated while you exercise from the space station. One of the early exercise devices they had that would really generate a lot of force got the solar panels actually flapping like the wings of a bird. And so isolation of these forces from exercise are super important. And so here's a video. It's not super high quality, but that's what NASA generated at the time. And you can see an individual that's pulling up with their hands, doing some squat-like exercise. They can connect these cables to the shoulder pads that they had, but pretty low intensity. So a lot of times you see this 3 to 6 days per week, really dependent on the crew member. But some of these astronauts were lifting weights, 6 days a week. And if you're doing 6 days a week of weightlifting, you usually are not doing it very intensely. And then the treadmill was somewhat limited in the speed. And as a result, it was just low intensity, moderate intensity exercise. And so what did we get out of doing that type of exercise, or what did the crew members get out of what we would refer to as a real high volume, moderate intensity exercise? And so taking the MRI images that were obtained from a group of crew members, focusing on the calf muscles because they are some of the most affected muscles of spaceflight. You can see this is with a lot of exercise. They still were losing on average, the size of their calf muscles was still down between 10 and 15%. Two crew members were down over 20%. So likely some benefit, but clearly it's not a very good investment because it's not being overly or clearly as protective as we want. We'd like them to come back with no loss. They don't have to gain anything. We just don't want them to lose. And their strength mirrored that. If we look at some of the data from the biopsy, the muscle biopsies that we took, again, one of the calf muscles that's really affected is the soleus muscle. It's on the back of your leg. It's quite large muscle. You can see when we isolate out those individual fibers and we measure the slow twitch or the endurance type fibers and the powerful fast fibers, the size is down around 30%. The strength of the fibers is down around 30, 40%. So clearly, while they're putting in a big effort, it's not a very efficient use of their time, clearly. And then we also looked at a series of those proteins or enzymes inside of the mitochondria, the powerhouse. And so this labeled here PFK is an enzyme that helps you use sugar in your muscle. And you can see the dotted line here is 100% of pre-flight. And so the slow fibers were able to maintain their ability to use sugar. The fast fibers lost about 10% of their ability to maintain sugar, to use sugar for energy, I should say. So pretty good, but still not exactly where we would like. Citrate synthase is actually part of the mitochondria as well that helps generate energy from both using sugar and using fat. And all of that moderate intensity exercise actually improved their capacity to do that. So one of the benefits of kind of overdoing it is in fact the training response. And this last one is a marker of our ability to use fat inside our muscle. And so they also increase their ability, 20 to 30% increase in their ability to use fat. So benefit, but likely, again, we don't need it to be going above 100%. And so likely spending too much time on this really moderate to low intensity exercise. And to give you some idea what that looks like from a functional standpoint, at the time all of these astronauts were going to space, they were coming back to Russia. And so this is a landing in Kazakhstan. This is one of the studies that the missions that we were involved with. Don Pettit's one of the gentlemen that will be coming out. And so you can see, if we think about going to Mars and being able to land on our own and get out of the capsule and pull the Matt Damon where he's walking around and doing the things that you may have seen in The Martian, you're not going to have 30 plus people or however many around here helping you get out of the capsule. But this is in Russia, so there's NASA members here as well as Russian Space Agency, Roscosmos personnel. So the first gentleman's coming out, being carried over to his seat. So that's a Russian crew member, and now you'll see the next individual being brought out of the capsule. You can see the helicopter in the background that's going to take them off. So this, again, gives you some idea of 2.5 hours a day. I think all of us, if we put 2.5 hours worth of time into exercise every day, we would hope we would come back looking a little bit better than this. Clearly can't get out of the capsule on his own. Struggles a bit here to turn around. And you'll see them bring him down the slide. Tough time getting his legs up. I don't think he's prepared to be doing this on his own. And I'm going to just let the video play a little bit till they get him over to his seat. And one of the things that is a real problem when crew members come back to the gravitational environment of Earth is blood tends to want to leave their head and move towards their feet, and they faint. And passing out or fainting when you're horizontal like he is, and you can see, boom, he started to pass out, and they lifted his legs up in hopes of getting some blood to flow back towards his head. So even somewhat horizontal, they're not even able to maintain blood flow to their head. So they're clearly not able to manage themselves, and all of that investment is not optimal. And so during all of these studies, you can imagine when you're studying only a few people and every time they go to space, it's a 6-month endeavor. We were doing a bunch of experiments on the ground to learn more about exercise regimens and things. So I'm going to try and move through, let's see where we are here on time, move through a little bit quicker to get through some of this. But we did a series of studies to try and figure out, could you do low doses of exercise and how potent would they be? So the first study that was done was a 21-day microgravity simulation on Earth, actually crutch walking with one leg serving as what we were looking at. And so we were looking at every 3 days. When we think back to those signals and how long the signals last, we figured, and what typical people do on Earth, that spreading this out to only 2 or 3 days a week is probably enough. So 6 sessions over 21 days, every 3 days. And we're focused on the thigh muscles to just stay, to keep it controlled in what we were looking at. And we had them come in, they did 3 sets of 10 repetitions, 2 or 3 minutes of rest in between each of the 10 sets, nothing fancy, which took about 90 seconds each time they were here of actual muscle activity. And this is what we found. So the group that we called ULLS, that would be a group that walked around on crutches, atrophied 7-8%, which is what we would expect over 3 weeks. But the group that did that very small amount of exercise didn't have any loss. And what we're looking at here is their thigh muscle mass with an MRI, and they didn't have any muscle loss. So small doses, high intensity, very potent at preventing the atrophy. So then we stepped into the next study, 35 days. Can we take the 3 weeks out to 5 weeks? Same thing, about every 3 days, 12 sessions. Instead of doing 3 sets of 10, we broke it into 4 sets of 7. It's still, instead of 30 contractions, it's 28. But essentially the same thing, 2 or 3 minutes rest, couple minutes rest in between each set, each set of 7. And each one only takes about 90 seconds, right, of actual muscle contraction. So about 17 total minutes of muscle contraction. So the group that didn't do anything atrophied 8-9%, which is what we would expect for 5 weeks. And not only was the every 3 days effective at maintaining muscle mass, we actually were able to increase muscle mass pretty substantially. So small amounts, highly effective, don't interfere with the adaptive response in between. Looks like it could be quite useful. So then we got invited to be involved with a 90-day bed rest study, a microgravity simulation study in Toulouse, France, in southern France, in conjunction with NASA and ESA, the European Space Agency. And so we took exactly the same approach, started on the 5th day of bed rest, and every 3 days, so that means 2 or 3 days a week, depending on the rotation, depending on the week, you were doing that resistance exercise, about 4 sets of 7 every 3 days. Again, it's about 90 seconds of muscle contraction, 35 minutes total of actually contracting your muscle. The rest of the time, it's not doing anything. And what did we find? About 20% muscle loss in the group that just laid in bed and didn't do anything. This is, again, just the quadriceps. And we completely maintained muscle mass with that very small amount of exercise, just 35 minutes of muscle contraction. So when you summarize this, if we look at the over here on the left, the 21-day, 35-day, 90-day studies, 10 minutes of total muscle contraction, 17 and 35, which I already highlighted. But this is how long they were actually in bed. So 10 minutes of muscle activity, 30,000 minutes of bed rest, 50,000 minutes, 130,000 minutes of bed rest. So the signal for exercise is lasting a while, and it's really potent. And if you look at the time between, so about a minute and a half of exercise, and then they take off 4,300 minutes or 72 hours, right? Small dose, a lot of rest, and you get a really potent effect. So again, all of this is happening while we're doing the in-flight studies where they're just low intensity cycling and running on the treadmill. And so with all of that information from the space flight not being very effective, the ground-based studies showing low doses can be high intensity can be super effective. We were involved in designing the next generation exercise program that they originally called IRATS, the Integrative Resistance and Aerobic Training program, and the NASA PR department didn't like that, so that didn't last very long, and they turned it into Sprint because it was higher intensity, more sprint-like exercise. This is Steve Swanson, one of our subjects running on the treadmill on the space station. So for the next decade, we studied a group of astronauts employing this new program that we designed along with NASA. And the first thing we did, well, at the same time, we were doing a bed rest study that was 70 days to simulate the whole program. And then we had crew members starting off on 6 months missions. So I'm going to present the bed rest data and wrap things up. We don't have all of the in-flight data done yet. We'll talk about that briefly, and that's kind of what's remaining here for the next few minutes, and then I'll take questions. So same bicycle ergometer, but a new resistance exercise device that I'll show you a little bit more on, and a new treadmill that really allowed us to do the type of exercise that we wanted. So here's the new treadmill. This is Chris Cassidy, one of our subjects, hooking up the belt that he uses for providing resistance to pull him down onto the treadmill. He can choose how much force he wants to pull himself down onto the treadmill. He'll hop up here and he'll start running. And the speed of the treadmill is such that he can actually sprint. He can do some higher intensity running, sprint running. So that gives us another avenue to do some high intensity exercise. And here's the resistance exercise device. And again, you will see how it isolates all of the movement and force production from the rest of the space station. This is Michael Hopkins doing a series of different exercises, but effectively you can target every muscle of the body with high intensity resistance exercise, the same type of exercise that somebody wanting to build muscle mass going into the local gym would do. So nothing overly fancy. And even, again, you can do lower upper body exercise, and you will even see Mike Fossum here coming up with a way to do some sit-ups. So what was the design of the study? Well, if you look over here on the left, the exercise, this is for the bed rest study. We were just focused on the legs. For the space flight, they were also doing upper body. So some resistance exercise, continuous aerobic exercise, and then some treadmill running. And if you look at the first day, what do we have them do? We list 35 to 60 minutes because there's setup time, there's rest in between the exercise, but ultimately only about 5 minutes of muscle contraction. And then later in the day, they do 30 minutes of aerobic exercise, just lollygagging along at moderate intensity, sometimes watching a movie or something on a computer, for a total of 35 minutes of muscle contraction on day one. Day two is just intervals on the treadmill, 12 minutes of muscle contraction. Day three, they're back to doing 5 minutes of muscle contraction with their legs, 30 minutes of easy cycling for a total of 35. And then they do some sprint treadmill running. That's a different style of sprint, just 30-second sprints instead of 2 minutes. So only 4 minutes of muscle contraction on day four, back to 35 minutes of resistance and some easy aerobic exercise. And then 4-minute intervals for a total of 16 minutes. So over the course of the week, 15 minutes of muscle contraction from resistance exercise, 90 minutes of moderate intensity aerobic exercise, 32 minutes of sprinting for a total of a couple hours, right? 137 minutes. So very focused. And the way that we recruited all of these individuals was, if you participate, all of the extra time that you have is yours. That we really didn't give this. NASA gave this to them. So the rest of the balance of their 2.5 hours could go towards anything they wanted, time off and doing other things. So that's how we drew people in. So let me give you a little bit of the data and then we'll wrap up. So if we look at, we were trying to maintain the mass of the thigh, of the upper leg and the lower leg muscles, because those are the ones that really atrophy with spaceflight. They really deteriorate. And so this is with the bed rest study. So we were able to maintain muscle mass. If anything, moved it a little bit upward. So that was a positive sign. When we look at the individual fibers that we isolated, what did the size look like? We more or less maintained both those endurance and the power type 2 fibers. The strength of the fibers were maintained, the speed at which they contract, the power that they can generate, all pretty much maintained with the program. So that was a real nice thing to see. And then looking at the energetics, their ability to use sugar, that would be on the left. We didn't quite hit our mark on this, so we need to modify maybe a little bit. These two here are looking at overall energy production and fat utilization, the ability to use fat in your muscle, maintained. And we pretty much maintained all of those micro capillaries, the vasculature that delivers blood to the muscle. So that was all very positive for the thigh muscle. When we looked at the calf muscle, so this is a cross section of your calf muscle. These are the two gastrocs on the back of your leg that you see. If somebody's wearing shorts, you might see the two out muscles that are sticking out. The soleus muscle is the one that kind of helps you stand upright when you're just standing, and that's this muscle here. We weren't quite able to maintain that. We've really struggled with figuring out how to maintain that. So we have some more work to do with that. But the exercise did maintain the type 1 fibers. The soleus doesn't have very many of those fast, powerful fibers because it's just there to help you stand up. It's not really there for much else. But size, strength, speed, and power of those individual fibers was maintained. So that was a positive sign, probably from the sprint running that we were doing. Glycogen, the ability to use sugar was maintained. The ability to use fat was not quite there. Probably need to do a little bit more, but the blood supply was maintained. So we're getting quite close, massively closer than we were on the first decade. So we feel like we got a real good program for the thigh, maybe tweak it a little bit. I think the calf needs a little bit more work. Probably something outside of exercise, something that they wear to put some force on their feet and their muscles all day. So I mentioned the ISS data from this. We're still in progress. We actually have doctoral students in our program right now that are preparing to do a bunch of analysis on all those enzymes of the powerhouse of the cell to figure out the energetics of the crew members' muscles. And our initial evidence from some of the other measurements suggests that the program was super effective. So we're quite pleased with that. So I'll wrap up with just a couple more comments. It certainly has been an interesting journey the last 20, 30 years working with the different crew members. This is Reed Wiseman. Here's a picture of my brother Scott and I with Reed after we've taken a sample from his thigh and calf. You can see the bandage around his calf. We just taken a muscle sample before he launched into space. But I bring this up because Reed is scheduled to be the commander of Artemis 2, which will be the first human mission back to the moon. They won't land on the moon, but they'll go around the moon. That's scheduled as the next flight, and he will be the commander of the next flight. So part of our data set from the last decade comes from Reed. So hopefully it's very clear small doses of exercise go a very long way. Incorporate that into your own personal health plan. And we think of this not only in the context of astronauts, but also in the context of programming for aging individuals, programming for rehabilitation from hospital stays and different surgeries and injuries. And so we think there's a lot of benefit to taking a lot of this knowledge. So a couple acknowledgments. Dave Costel, who founded the Human Performance Lab here at Ball State and started the whole involvement with NASA back in the early 90s, along with Bob Fitz at Marquette University. This is myself with them when I was a doctoral student in the science mission control. This is my brother Scott, who's been a partner in crime in all of this since 1992. And our colleagues at NASA, Lori Plout-Snyder and Jeff Ryder, our colleagues in Europe and at Karolinska in Sweden, and Kirill Minchev, who is here in the Human Performance Lab, and the tedious work of isolating all those individual fibers for all these studies. He has been the one driving all of that for the last 20 plus years, so he deserves a real shout out. So I'll leave it there. May have ran over a little bit, but we still have about 13 or 14 minutes for questions. We have a big group here at the lab of graduate students and other workers that help keep everything running, and I acknowledge them and be happy to address questions if you got any.
I have a question. So in the when you showed the three tests, what I think it was 10-day, 35-day, and 90-day tests, you said, I think, unless I misunderstood what you said, but during the 35-day test, you actually saw an increase in the muscle strength, but in the other two tests, there wasn't really that growth. So I was wondering what the difference was that made such an improvement.
Yeah, fair question. Don't know the answer. Um, That's a very good question. The 21-day study used a standard weight stack device. The 35-day study used a little bit different device that was designed to fly in space, and I didn't get into all of that. That probably loads the muscle a little bit different and a little bit better. And so I think the difference between the 3-week and 5-week study was that. And then going out from there to the 90-day, my guess is because they were using the same device between 35 and 90 days. The fact that it wasn't as effective is my guess is as we get out and go a lot longer, the signals for atrophy and such are much greater, and the program probably would need to be altered if the goal really was to grow. So yeah, I'm just speculating. It's a great question. I officially don't have the answer for that, but
Okay. Well,
yeah.
thank you.
Yeah. But I appreciate it because I see that when I look at those graphs, so I know you're paying attention. That's great.
Yeah, I thought that was interesting. So thank you.
Other questions? Don't have to be overly deep science. They can be, but they don't need to be.
This is Amy. So I have a non-deep science question for you too, and just thinking about how, you touched on this briefly on your last slide, but how we use some of this to inform even practices like in the workplace. So I think about it, I'm far too sedentary most of the time, just staring at my computer screen. And what this seems to suggest is maybe if there were a place where I could go lift some heavy weights for just 5 minutes, I could see some long-term benefit that in terms of how my body's aging and things like that. Have you thought about like what some of those implications may be for just how we structure our environments and how we could really take advantage of this fact that it may not be this hour-long thing that we learned since we were young?
Yeah, I think that's exactly how I would hope you would interpret this. Um, and from the individuals to motivate you to do something, to realize that the signal is potent, and you don't need to be exercising. You can exercise for a long period of time, but you don't need to be. Um, for the administrators and others that allow us time to do these things or not, hopefully they hear the message. And I think that's the take-home message is how powerful the signal is. We've been involved with another study for the last 10 years that's really trying to understand all of the signals on pretty modest amounts of exercise. We've been studying for the last 10 years. That's just wrapping up this spring. And I think that's the message. I mean, something is better than nothing. That's clear. It's very clear. And there's studies that even show if you look, I'm just looking at muscle mass here and talking about that, but blood pressure regulation and stuff, standing uh, alters your regulation of blood pressure in a positive way. So obviously we'd like people to do more to some degree, but any amount has some impact. There's no question about that. So I think that's the take-home message. I think as we were talking at the beginning in relation to swimming, we have a lot of data related to this for tapering for swimming and I was a sprint swimmer when I was in college, and the amount of exercise we did would be comparable to that first 10 years on the space station. It was just overdoing it. And it's pretty amazing to look at this approach as you think about even applying it to athletics, that the dose that an athlete needs, if it's the proper program dose, is probably a lot less than people think. So I think it has implications across, and we do a lot of this with aging individuals as well. I think it's super effective for older individuals, highly potent. So that's exactly the take-home message. Spread the word. Other questions? I see a few students on here. Must be some student with a real zinger of a question.
I've got an easy one, probably.
Go for it.
Overall, would you say throughout the NASA studies, was the goal usually always just to maintain muscle mass?
Yeah, yeah. It was 100% to just maintain. All of the crew members, at least, are pretty active. They're not, some of them are highly active, but I think if you take an average, they're moderately active individuals that do something most days of the week. And the whole goal is they're fit, they're healthy, and if we can maintain all of their physiological systems and health parameters, that's the goal. There's no reason to go above that. And we've yet been able to do that, but I think we're getting pretty close on most of the systems now. But yep, that's exactly the goal. Other questions, thoughts, comments?
You anticipate future NASA studies to finalize the official goal and meet, since you said we're pretty close to where we should be?
Oh, that's a loaded question in today's political environment. I've been talking with a few of our colleagues that work down there, and similar to other elements of the agency, there's been discussion of NASA-wide cuts to staff and things, as well as they've talked to Boeing already about cutting that Artemis 2 mission that I just showed you with Reed Wiseman. So Depends on if NASA stays intact and if funding stays intact, but we would hope that once we get our data published from all the crew member findings that we have, that we would hopefully be kind of front runners to be involved in the next series of studies. Maybe we'll have to go through SpaceX to get our funding and interact. Maybe they're the ones that are going to be driving the long duration missions to Mars and stuff. But I think we're definitely at the forefront of defining the scientific understanding of the exercise countermeasures for the crew members. So if there's an interest by the federal government or commercial interest, I would like to think that we would be part of the team involved with that and answering those questions. I think we got the technology and the team to do that, and the track record of delivering on it. So I hope the answer to that is yes. Got a couple more minutes. Other questions, thoughts? Fun stuff to talk about, at least for me. We're doing a lot of, well, a lot. We have some other studies we're doing over here where we've gone back and we're reanalyzing some of the MRI images that we've collected on individuals. One thing that I didn't spend time talking about today, but what we found is one of the studies that we were asked to be involved with was a all women study. And it turns out that less than 10% of all of the individuals that have been studied in Earth-based studies and in spaceflight studies have been on women. So the amount of knowledge that we have is fairly limited, but the number of women flying in space is really getting ramped up. And it's hard to believe that it won't be a woman that's the next person to step foot on the moon if and when we go back. But one thing we have found is that the responses of women, at least if their muscle mass and their individual fibers is substantially different than men, they seem to be to atrophy a lot more and lose a lot more of their muscle mass. We have a graduate student right now working on that as part of her thesis project. And so it looks like they're super responsive to exercise, but it also looks like they need some different consideration from men. Not surprising when we really think about things, but it's something I think NASA needs to really focus on. And we'll be publishing some papers to try and push that message along. But that's another element that has not been explored too much in NASA. It's been a fairly male-dominated group of astronauts.
Looks like we're about to hit our time. So I just wanted to thank you, Todd, for sharing all that. That was super interesting. And thank you everyone for attending. And just as a reminder, our last virtual lunch and learn of the year will be on March 20th and feature Dr. Lisa Davia Rubenstein, Professor of Educational Psychology here at Ball State. So look forward to that. And thank you again, Todd.
Thank you, Nick. Thank you everyone for coming.
Thank you so
Thank you.
much.